This video is brought to you by mywayteaching.com.
Next, consider problem. 2 liters of an ideal gas at a pressure of 10 atmosphere. It expands isothermally into a vacuum until its total volume is 10 liters. How much heat is observed and how much work is done in the expansion? Okay, solution I will write here. So we know that Q is equal to minus W is equal to PEX 10 minus 2, okay, is equal to 0 into 8. We get 0 only. No work is done, so no heat is observed here. No work is done, so no heat is observed. No heat is observed. 10 2 liters, here they have given 2 liters of an ideal gas at a pressure of 10 atmospheric pressure. So you are 10 minus 2, that is 8, where the exp pressure, external pressure is 0 into vacuum until its volume is 10 liters, means its volume become 10 liters, means again the external pressure and internal pressure both are same, that's why px is 0. How much it is produced? So no work is done, so no heat is produced. Okay, next question. Consider the same expansion, okay, in the what I given in previous example, but this time against is constant external pressure of 1 atmospheric pressure. The same thing we know. uh, we know that Q is equal to minus W is equal to you know PEX, external pressure they have given on atmospheric pressure. We know that is 10 minus 2 is equal to 8. PEX is 1 and this is 8. How much you are getting? 8 liter atmosphere. 8 liter atmospheric pressure we got. Okay, next. Consider the same expansion to final volume uh, of 10 liters conducted reversibly. So we'll write down the solution. We know that Q is equal to minus W, or 2.303 into 10 raised to log 10 by 2. That is your, after calculation of this, 16.1 liter atmospheric pressure you are getting. Okay, next concept is enthalpy. Okay, what is enthalpy? In that, first, a useful state function. Okay, we know that the heat observed at constant volume is equal to change in internal energy delta U is equal to QV. Okay, but most of chemical reactions are carried out not at constant volume but in flask or test tubes under constant atmospheric pressure. We need to define another state function which may be suitable under these conditions. Okay, and we can write the equation. We can write the equation delta U. We know that delta U is equal to Q plus W. This equation can be written as delta U is equal to QP minus P into delta V at constant pressure, where QP is heat absorbed by the system. QP is equal to heat absorbed by the system. Okay, heat absorbed by the system QP, and minus P delta V represents minus P into delta V, which represents what it represent expansion work done by the system. It represents expansion work done by the system. Okay, so you this is at constant pressure. Okay, next let us represent the initial state by subscript 1 and final state by subscript 2. That is initial state by subscript 1, then final state by subscript 2. Okay, so we can write equation u2 minus u1 is equal to qp minus p of v2 minus v1. Okay, so again on a rearranging, we get qp is equal to u2 plus p v2 minus u1 plus p v1. Okay, now we can define another thermodynamic function, the enthalpy H. Another enthalpy function H, this is called enthalpy function, that is Greek word H, enthalpy, and to warm or to heat content enthalpy means. Okay, so now you can write H is equal to U plus PV. Okay, so equation this we called as equation 1. Equation 1 becomes QP is equal to H2 minus H1 is equal to delta H. Okay, next, although Q is a path dependent function, H is a state function because it depends on U, P and V. P is a dependent function. P is equal to path dependent function, where H is equal to state function because it depends on, because why it is called state function, it depends on U, P and V, all of which are state functions. Therefore delta H is independent of path, hence QP is also independent of path, all of which are a state function. That's why delta H, it is independent of path, independent and of path, like and also QP is also independent of path. Okay, so for finite changes at constant pressure, finite changes at constant pressure, we can write delta H is equal to delta U plus delta PV. Okay, so since P is constant, delta H is equal to delta U plus P into delta V. It is important to note that when heat is absorbed by the system at constant pressure, we are actually measuring changing in enthalpy. Okay, at constant pressure, we are actually measuring changes in changes in the enthalpy. Okay, so remember delta H is equal to QP. This is observed by the system at constant pressure. It is observed by the system at it means observed by the at constant pressure. Okay, next delta H is negative for exothermic reactions which evolve heat during the reaction. Delta H is negative. Okay, so for exothermic reaction during even heat is during the reaction, and delta H is positive for the endothermic reactions which absorb heat from the surroundings. Okay, which absorbs heat from the surroundings. And now you consider at constant volume, cons constant volume means delta V is equal to 0. So that delta U is equal to QV. Therefore, equation delta U is equal to QV. The difference between delta H and delta U is not usually significant for systems consisting of only solids or liquids. Solids and liquids don't suffer any significant volume changes upon heating. Okay, the difference however becomes significant when gases are involved. Let us consider a reaction involving the gases. Let us consider let us consider gases involving reaction involving gases. If Va is the total volume of the gaseous reactants, Va is equal to gaseous reactants, and Vb is equal to total volume of the gaseous. Everything is same, but it is for products. Na is the Number of moles of gaseous reactants. Number of moles of gaseous reactants, where NB is equal to number of moles of gaseous products at constant pressure and temperature. Then using the ideal gas law, so which is at constant temperature and pressure, using the ideal gas law, PVA is equal to Na into RT, PVB is equal to NB into RT. Okay, so PVB minus PVA, if you are subtracting, this is equation 1, this is equation 2. Next you are subtracting PVB minus 2 minus 1, so NB into RT minus Na into RT. Here you are taking RT common, that is NB minus Na remaining, and you can write this as P delta V is equal to delta, this one Ng, this one you are writing RT here. Okay, so here delta Ng refers to the number of moles of gaseous products minus number of moles of gaseous reactants, this one only. Okay, we're substituting the value of P delta V in equation, this value, this is consider equation A, so this is put in equation delta H is equal to delta U plus delta Ng, wait, this can be in delta U, and in this equation 6.8 we get when del P delta U delta Ng RT. Okay, this can be put in equation, wait, this can be put in equation delta H is equal to delta U plus P into delta V. If you are putting this one equation delta P delta V value, so you are obtaining delta Ng into RT. Sub A in this equation. Okay, so now the equation, now this equation is useful for calculating delta H from delta U and vice versa. Okay, so this is about a useful new state function, enthalpy.